Do that. Hello and welcome to Lecture 11, Part 1. We in the prior lecture saw some introductory functional programming constructs, particular map, for each, and zip. And we're going to cover a couple more in this lecture. Um, so, uh, what is this today about? Actually, today's more about reduce and fold or the operators, but more so what happens when we want to downsize, right? So if you think about map and for each and zip, all of those, the number of input things is the same as the number of output things, right? I applied function one by one. Reduce and fold are ways to take a collection of n things and somehow get one thing out the other end. So let's fire up the notebook. Good to go. Right, like I said, so we previously just talked about doing things one-on-one, right? What if we need to combine and collapse things, right? And collapsing sounds easy at first. Oh, that makes sense, right? But then there's some nuances, right? Um, what order do I apply these collapsing operations on? Which elements? And also, I want to be graceful, right? If I am asked to handle an empty collection, what happens, right? Let's say I want to handle a collection that has only one element, and my collapsing operator requires two elements, right? Two arguments, right? It's a binary operator. How does that work, right? So, um, let's talk about that. So the first one is reduce, right? And I think people often heard this word in their periphery if you haven't learned functional programming before, because you may have heard things like, Google's map reduce framework, right? Map reduce. As an aside, for those listening, Google's MapReduce, the reason why they chose that naming is it has both map and reduce. The name is too concise. There's this middle step that shuffle is really important. People will lose track of. And there's some other differences too. So, other than that simple name similarity, I would think of reduce as a more general, a different kind of concept. But, anyways, with reduce, given a binary operator, keep applying it on the collection until you're down to one element. So you can imagine, hey, given a collection, let's just say a seek of 0 through 5, I say, hey, I want to reduce that, right? So I could say, hey, reduce. So um, these are all elements, and now this reduce operator, like I said, it's taking a binary function, a binary operator, right? So notice how it expects two arguments, right? Um, and then I'm adding them together, sure. Or I can use that spiffy placeholder syntax. So this is going to be A, this is going to be B, right? So the reason why I can do it here and I couldn't do it before is I actually have two arguments. This is the first argument, this is the second argument. Cool, that checks out. Um, Now let's say I wanted to, okay, compute the squares of things, sure. Now sum of squares, I could simply, yeah, apply reduce onto the squares. Yeah, that checks out. Um, or I could use all in one line without even naming things. In this case, you have, literally map and reduce going together, and it gets the same result. So far, it seems like, kind of we're hoping to get. Questions so far? Okay, so uh, let's try to make reduce go to work for us. So it's already resolved just a few minutes ago. Here's the original code. What we're going to target with this reduction thing is this reduction. So hey, guess what? Remember I said this is an OR reduction? We have a reduce operator. We just want to put these two together, and the answer is yes. We can go ahead and we're right here. So here it is. Great. So here we want the OR reduction of those operators. So before we had to grab the invalids with the map, and then we had to, do all this typecasting, or I could just do this. Right? I can say, hey, given all these things, reduce. Um, and that works. That's pretty cool. So reduce is really helpful. Uh, but of course, there's got to be a gotcha somewhere, right? And the question is, what happens when you give reduce zero elements, or even just one element? Um, or what happens if I want to collapse a collection that's one type, and the output is going to be a different type? So somehow I'm changing things, right? And so, like I said, I would think more generally about these constructs. Rather than thinking about this in terms of, these simple examples of integers, think about more as kind of the more general pattern. The more general pattern is I have n things, and I want to apply a function to these things somehow boil this down to a single result, reduce it down to a single result. And so we kind of see that play out. So enter something called fold left. So this is another operator. Uh, from the name fold left, you may wonder, is there fold right? Yes. We'll come to that later. uh, and so what does it do? It's similar but different than reduce. I have a picture for this, not for reduce. But um, what we do is, so with reduce, we took two elements at a time, applied it, got a result, and then we took that and kind of kept going through. With fold left, we're going to take this initial element. So this initial thing you give it, in this case, you can see I give it 0. There's actually a separate argument, and then the function. So what does it do? It takes the thing you give it and the function and applies one by one, right? So maybe it's more clear if I show you here. You have this init, this thing you give it initially, you give it a function f, put these two together, you get an output. Then an output is then applied to the function again. So you can see that kind of it goes through it. And eventually the result of this we get is a single output. So even if the function was applied n times, um, we only get one thing out the other end. And what we're doing is each time we're taking this kind of current value of init element and applying it. Now, with regards to fold left versus fold right, I've drawn this such that fold left starts from the left and fold right starts from the right. That was me deliberately tweaking the choice of how I drew the array. If you put the 0 on the left of the array, then yes, this works out that way. If you put the 0 on the right, perhaps like you do like numbering bits in a number, different endianness, you're going to get the opposite direction. So the way to think of it more generally is your default model should be fold left, and that's starting from 0 going up. Fold right starts from the end and coming down, right? So you think about your for loop just right as not functionally, you're probably going to say, for I equals 0, and then you're working I equals 0 first. And so full left's going to give you that same behavior. So it's kind of a good default in your mental mappings. Yes. The question is, are fold left and fold right implemented differently? How does that work? So yes, you can call reverse on the input to one of them to get the other one. I believe the actual Scala compiler is smarter in that. But yes, if you forget fold right, we'll see an example that you can call dot reverse instead. Um, so let's actually play with this, right? Um, and so what's nice about fold left is kind of a more general operation. It's probably one you use more often. However, there's cases where it's safe enough and you can use reduce. I use it reduce because it's more concise, right? So the part of the challenge of fold left is not just the operator. So reduce required just the operator, a function. Now you also need to give it the init value, right? So okay, give it the init value, give it the function. So um, let's say, for example, I just want to add things up. Well, what would I do? I have this function. Remember, this function takes in two arguments, right? What's two arguments? If you go back to the next slide, right, you have this init value and the element you're being given from the collection, right? So I labeled them hopefully more clearly, right? Total so far and elem. All right, great. So we're just adding them up. So the result of this is going to be some, int from the addition. That's going to be passed on to the next thing, right? So we're going to pass it on, you know, down this chain. That's going to become total so far next time it's invoked. So here I'm running this out very painstakingly verbose. I can use that placeholder syntax. I can also use reduce. And because Scala is Scala, there's also just a dot sum, which applies the plus operator to your collection, which is interesting because you can have your own classes and you can define addition on them and then call dot sum, even if it doesn't make mathematical sense to think of them as adding, but you can take advantage of that feature to call a reduction on the add operator. Cool. Okay, so I can show the next thing with the fold left in a second, but before that, questions so far? These are some of the shortest lectures of the quarter, but I deliberately have not put content into them because this is like the most conceptually tricky stuff. And so we can pause and talk about it. Yeah. That can be a different type than the element. In this case, it's the same type, but it could be different. Yeah. Yeah. So initially we have this init, which is zero, and that the first invocation total so far is going to be zero and then the first element. So we get I equals zero's element, and total so far is equal to zero, and then we get some result. That's the new total so far, and it comes in here, and then we have the I equals one element applied to it. So index of element is I zero through whatever as it goes through it. Total so far is that thing kind of being passed along. It's kind of like a carry chain and like a hardware, and so that's kind of what you're seeing there. So it's kind of think about this construct, right? Let's say you're writing this. Uh, you know, my slides are pretty impure. But what if I was to soil them by saying var, you know, for x in L. Actually, I have to do. It's not Python. I'm sorry. Um, then I could say total so far plus equals x. I think this is gonna work. Yeah, right. So it's kind of what we're doing, right? So I had to make var, I had to make total so far a var to kind of show it's mutating. In this case, that mutation is encapsulated by this functional programming operator, right? Um, the function is a pure function, right? This function I defined simply takes two elements and adds them together. The fact that, each invocation is given a different argument, different value for total so far, that detail is hidden from the person writing this. That's done by the fold left operation, kind of pulling it all together for us. So yeah, we can kind of see a few different ways of writing this, right? We can write it like that. We could even be naughty and say L for each total so far plus equals this. Will this work? Fingers crossed. Also works, right? It's a robust language. um, guess what? We don't need to do this because we can call reduce, fold left, or even the sum in this case. Sum because of the plus operator, but you can imagine, of course, we aren't just doing integers in the real world, and that's not always possible. Cool. Now let's see my attempts at max down here. So down here, I'm trying to write a way of finding max element. So what do? Well, we have this function which has a max so far, and given a new element, returns the greater of the two, right? Whichever one is bigger, I'm going to return that. So if max so far is bigger, that's what we get. Otherwise, that, sure. So like I said, max the hard way. I'm using fold left. So I'm saying originally let's assume there's at least some positive integers, so zero is not a bad starting point. And yeah, we just give it the function. Cool. And yeah, so we get maximum element is 5. Scala also has a built-in dot max. That's nice. But we're seeing fold left applied, right? So in this case, we're going through it. Cool. Yes, question. Yeah, so do chisel vex have fold left? They should. And let's say I forget if they do. Let's use the power of a more complete programming environment to answer that question. Dot. So now we can see all the things defined on this vec. So do we have fold, and do we have a reduce? Yep, we got reduce. So yeah, the answer is yes. um, they said that's because the chisel library implementers implement those functions within those collections. So these are operations that each class is implementing. And because this is a common pattern, we as a outsider can say, I don't even know chisel vex, right? But I know what map means, and I can use map, right? So it's kind of point. So that's the power of having a pattern, right? Is that you can kind of reuse this concept over and over again, even though it's technically different code and stuff, right? That's definitely the goodness we want. Cool. Actually, I'm going to use this opportunity to do an example of, okay, let's say I've sold you, and you say, hey, I want to use fold right. What happens? For some of these, it's really not going to break too much because left versus right can only change the result, right? Addition's, associative, so that checks out. But just for the sake of trying it out, let's see what's gonna happen. So it's gonna let me do it just fine. This is glossing over an important difference, and that is that for fold right, the order of these two things coming into the function are flipped. So this works out because it's associative addition, right? But uh, with fold right, it's actually element and then total so far. Yeah, you can argue that either way, but they chose to make that choice. So we'll see that in a second with an example bit of code. Okay, so then um, we have so much time, so I feel bad cutting this off halfway. I'll take a question. Oh, it's a question. Perfect. Yeah. So your question is: are fold left and fold right in the chisel vec are they recursive in their implementation? So the question is specifically about tail recursion. The reason why I'm pausing is because what we care about is there's the execution as the generator is running, and then there's the hardware that gets materialized, right? And so um, if you think about it, if you're calling fold left on something that's going to become hardware, what you're saying is each function location is doing some sort of operation, and those operations are going to be, creating some sort of lattice you're rebuilding in hardware, right? And so, um, yeah, I'm not sure if the tail recursion notion is really visible, I guess, because normally the whole point of tail recursion is, oh, that's great. I can be really clever in my implementation of the software and I can get some nice efficiency gains, right? But in terms of hardware, uh, well, yeah, but I guess also this is maybe a question turning back to you, right? Like, would fold left already on its own kind of be tail recursive, right? Because you're forced to like be explicit about what you're carrying on for each thing, and you can't do work after you do one element and then you're done with it. You can't touch the element anymore. Now you're on to the next element. So I feel like it kind of already is tail recursive. I'm saying I have a question mark 'cause I'm not a PL person, but um, to me, full left at least has the spirit of being tail recursive, if not formally so. Um, Good question. Okay, so I'm going to do one bonus slide and then we're going to stop early, and then we'll also have a shorter lecture on Thursday. I'm debating between like doing two today and one Thursday. I think continuing to cut in half is still the plan, so we're going to do that. Okay, so we've seen the syntax. We can talk about a little bit, right? So something called currying with regards to functions, and that is the ability to break up your argument list into multiple privacy blocks. So at first, that may not seem very helpful. Like, why would I want to break up? Remember, we did the seek.fill earlier, right? And this is the number of elements, this is the thing. So why was that a feature? The reason why it's a feature is we can do partial application of functions. So I can apply one function block, one set of arguments, and leave the other set of function arguments unapplied. So let's kind of see this play out. So I could define two functions, sum and plus x. So they both add two numbers. So in order to get a number out the other end, at some point you're going to need to give it two numbers, right? That's inevitable. Now, what's interesting is uh, if I take the second version, which has the argument split up like this, and I do it like this, we saw the syntax earlier today, right? This is a function that takes an int and it is returning an int. When we look at the definition for plus x, ultimately it has two int arguments. So what the heck is going on? Well, we're partially applying this function, right? So we're applying this one to be here, and so it gets plugged in here. And so as a result, this f is going to add one to whatever we do, right? So we say plus one, and so it does that. So the way you don't think of this is like a function generator, right? We have like a function, and this function, we're gonna populate some of its arguments now, and the other ones we're gonna leave unbound intentionally, so that way we can go ahead and apply them later on. So yeah, of course I can, directly apply them both from the beginning. That's fine. But the reason why we're excited about this is we can do things like this down here, where I can create a function, populate its arguments, and then so remember this is going to be a function that still has one argument unbound. Guess what? For map, you need a function that takes in one argument. So now I can apply this to there, and I can add, in this case, plus 10 to all of them. Yes, questions? Yeah, that's a great question. So what about this underscore here I have over here? I'm pretty sure if I remove this, it's going to break. Let's see what it tells us. Yes. So what it's telling us is, hey, you're trying to call this function, and I didn't get all the arguments. And so here we're saying, you know what? I didn't get all the arguments. Still, right? You'll get it later, right? um, and then, of course, if I try this on sum, no chance, right? Sum says it takes two arguments. I only gave it once. So by breaking things up, we can do this. And the reason why you break it up is because you're going to, at some point, partially apply it. Now, um, so why does this syntax work down here? So what's happening is this is being partially applied. The result is a function. So plus x becomes like a function generator in a way. And the result is a function, right? We get back a function that takes in an int, right? Given an int, this will now give me a new function, which given an int adds them together, right? And so because I now have, this is producing a function that gets plugged in immediately into the map, it's happy. In this case, they made a choice that this is not unclear. So you need to mark it as chill for the other placeholders. Cool. Yes. Questions? Oh, so why is plus x and sum different with their behavior in its partial application? It's because of this parenthesis block. So the parenthesis block, they need to be complete. You can't have a partially complete block. So um, you can do that. Now, let's try to MacGyver something. What if I said, hey, I want to make a function which is, my plus x. So I'm going to use the same technique we just saw, but then internally use sum. I think that's totally fine, right? Yeah, that's totally fine, right? So the key thing is, yeah, in Scala, these privacy, braced argument lists need to be complete. So you can't have only some of them, unless, of course, you made one of them, let's say, like a default value or something. But that's different, right? Um, so occurring, you can break it up into multiple groups. And the reason why it's useful is because you can do partial application. We'll see an example of this in the second half of this lecture, which will be a different day. But yes, yeah. Oh, great question. Yeah, so I'm gonna repeat this for recording. So if I have multiple argument blocks, I'm kind of slightly rephrasing it. What is the application order? How does that work? I believe it is left to right. You definitely can't skip them. So if I had like say like a third or a fourth one, if I just what the town on this, I couldn't do like this one, but not this one. I think it's left to right. And now I'm trying to figure out a way I can try and differentiate that. What would be a clever program that show a difference? Oh, I know. What if I made a function that took one of each, right? So I guess what if we had something that said, hey, this is a silly function. Let's say it takes in a string and an int, and I don't know. We're actually not even use the string. Okay, so we define silly f, and then if I try to say, hey, silly f2, plus not even the right name. Oh, I really broke it, but I think we're gonna keep trying anyways. Um, you can see that, yeah, it's going to apply from left in to out, right? So it's trying to do the string first, and that's not going to work because hey, it says it wants the string for that first argument block, and I'm giving it an integer. So yes, if I said aha, um, then of course I need to have that syntax. So yeah, so to answer your question, which we just kind of rediscovered on our own, because we forgot, you can't skip over any blocks, and it goes from left to right, from inside to out in a way. If I use the underscore as a way to skip over it, um, I don't think so. I think it's one of these things where when you design your functions, you probably need to declare them in the right order, but there's always some wrinkled skull I didn't know, so it may be possible. Um, there's a whole set of functionality and language you don't even cover it all in this course about lazy evaluation. And so, uh, yeah, then there is some kind of workaround to do what you're describing, and I'm not quite sure how to do it. Um, but fortunately for Chisel, right, we're trying to write hardware. We're not necessarily trying to do the most, obscure Scala. We're trying to make hardware that makes useful generators. So we have this kind of very utilitarian perspective of, does this let me write code either more productively, as in less time writing, easier to get correct, or easier to read. It doesn't help any of those three things. We're probably not going to be embracing it. Um, cool, great questions. So yeah, I think rather than sprinting to finish, we're just going to park it here for today, and then we'll pick up on Thursday.